Great. Well, we are very excited to have Anna Maria here to tell us about some really cool work connecting a variety of physics programs that I'm certainly excited to hear about. Whenever you're ready, Anna Maria.
Okay, thank you very much, Seth, for the invitation. So I'm going to be talking about some recent work with Nima Arkani Hamed, Monica Pate, and Andy Strominger. So let me start with some motivation. So the idea here is that there's been some progress in the past couple of years in understanding the asymptotic structure of gravity and gauge theory in four-dimensional asymptotically flat spacetimes. And I would say that the program sort of started with the work of Andy Strominger and collaborators, who first noticed that soft theorems in gauge theory and gravity can be understood as conservation laws associated with large gauge symmetries. So there is this connection between soft theorems and asymptotic symmetries. Now, in particular, one aspect of this story is the fact that the subleading soft graviton theorem, which I'm going to be briefly discussing in a bit, encodes more than the expected Lorentz symmetry of scattering amplitudes in quantum gravity. It encodes an enhancement of the Lorentz group to full Virasoro. And in particular, one can use the subleading soft graviton theorem to construct an operator, or rather subleading soft graviton mode, whose insertions in the S matrix element in S matrix elements obey the Ward identity of a stress tensor in a two-dimensional conformal field theory. So this kind of observation from a couple of years ago tells us that perhaps one might be hopeful that there exists some kind of duality between a theory of gravity in 4 dimensions and some sort of perhaps exotic conformal field theory living on the two-dimensional celestial sphere at null infinity. Now, this observation is actually not that new, and it dates back to at least, the work of De Boer and Solodukin from about 20 years ago, who used some clever slicing of Minkowski space in terms of de Sitter and anti-de Sitter slices and then applied the standard ADS CFT correspondence to each slice to kind of postulate that Minkowski space in 4 dimensions may have some description in terms of a theory living on the boundary of these slices, which in our case, we're going to see it's going to be identified with the celestial sphere. Now, 3 years ago or so, these ideas of De Boer and Solodukin have been made a bit more precise by Pastursky, Shah, and Strominger, who had this idea of just finding solutions to the scalar wave equation, which transform covariantly as conformal primaries under the Lorentz SL2C. And so this work of Pastursky, Shah, and Strominger triggered more and more interest into the so-called celestial amplitudes, which, as we'll see, are nothing but conventional scattering matrices in quantum field theory expressed in a different basis. So instead of working with asymptotic states, which are the standard momentum eigenstates, we will be interested in objects which are expressed in a basis of boost eigenstates instead. Now, the outline of this talk is going to be as follows. So I'm first going to spend some time reviewing this construction of celestial amplitudes.
Sorry, Anna, I feel that you might not be actually sharing the slide there you're actually using right now to talk, because we are still seeing the first page of the slide, just in case if that's not.
Oh, no, I just moved to, let's see. Sharing is paused.
Unless that's the problem only by myself, but anyway.
No, I think you may be right. I'm going to stop sharing and I'm going to share again. Good. Sorry about this. Share.
Aha.
Can you see now?
Yes, now,
yes,
yeah, right.
Thank you, Samu.
Sorry. So did you see the slide?
No.
I'm sorry.
No.
When I was, someone should have.
That's why I have a feeling that you might be saying a lot, but without
Yeah, I'm really sorry about this. So
Oh,
I was
good.
I was pointing towards these points. So hopefully,
Okay, great.
this was more or less motivation, but I'm gonna be describing this. So please shout out, like I'm gonna be changing slides. So if
Will,
you don't
will.
see them, then please let me know.
Yes, will.
Okay.
Thanks.
And thank you for pointing it out. Okay, so can you see now I have the slide with the outline of the talk?
Yes.
So I'm going to start off by introducing celestial amplitudes. And in particular, I'm going to be describing how one can go from the spaces of momentum eigenstates to the spaces of boost eigenstates or conformal primaries. And I'm going to be describing some properties of these celestial amplitudes. And then I'm going to go on discussing some results in this work, namely, we're going to see that properties of scattering amplitudes in momentum space imply some interesting properties of the celestial amplitudes, in particular regarding its analytic structure in the complex boost weight plane. And moreover, I'm also going to say some words about the celestial version of what in momentum space in quantum field theory is known as a soft hard factorization. We're going to see that there exists a celestial version of this idea. And moreover, I'm going to be describing some like a way to construct infrared finite celestial amplitudes. Okay, so to begin with, so an asymptotically flat spacetime is a spacetime which looks just like Minkowski space as you go to infinity. So here we have a Penrose diagram for Minkowski space. So this is a diamond. Each point inside the diamond is labeled by these coordinates x mu, which can be expressed in terms of spherical Minkowski coordinates r and z and z bar. So this z and z bar are just the usual angles in spherical coordinates, but after stereographic projection to the plane. And this u coordinate here is a retarded time. So it's basically the difference between the usual Minkowski time and the radial coordinate. So we have each point in Minkowski space can be expressed as a linear combination of these two null vectors. Now, the idea of this Penrose diagram, just to remind everyone, is that it preserves the causal structure. So in particular, null vectors or like null lines remain null, while distances are distorted. Time-like lines remain time-like, space-like lines remain space-like, but distances are distorted. So an example of this is this red dotted line here, which is a line, time-like line of constant radius, r. And so if we take the limit as r goes to infinity for either fixed retarded time u or fixed advanced time v, one reaches one of the two boundaries of Minkowski space. So these are called future null infinity or scri plus and past null infinity or scri minus. So in particular, I should also say that each point inside this diamond, actually each pair of points represents a two sphere. And the sphere we are going to be most interested in this talk is the celestial sphere at infinity. So this is one of these cross sections here represented in blue. And points on the celestial sphere, again, are labeled by these two coordinates z and z bar. Okay, so how do we go from momentum space amplitudes to celestial amplitudes? The idea is to start off with a scattering amplitude in momentum space. So for simplicity, we're going to restrict to massless scattering, in which case we know that the scattering amplitude is going to be a function of, in general, n momenta. So if you have n particles scattering, the scattering amplitude is going to be labeled by the respective momenta. And each momentum, each on-shell momentum is parametrized, can be parametrized in terms of an energy and two angles. Or a point on the celestial sphere. So this is the parametrization we're going to be using in this talk. So this is the same vector before, it's a null vector, and this omega here is the energy of the particle. And epsilon I is just a sign labeling a particle as incoming or outgoing. Now, we would like to take the scattering amplitude and express and construct from it an object which just lives on the celestial sphere. Now, using this parametrization is already clear that each asymptotic state is already labeled by a point on the sphere, namely the point at which either an incoming or an outgoing particle pierces the celestial sphere. However, in general, right, these amplitudes are also labeled by n energies. So what do we do about these energies? We'd rather have them be traded for some kind of scaling dimensions. Just in analogy with conformal field theory, where we have correlation functions being labeled by basically operators being labeled by a point on the sphere and some kind of scaling dimension. So it turns out that the map from momentum space amplitudes to celestial amplitudes is given by this Mellin transform with respect to external energies, with respect to all of the external energies of the particles. So naively, the intuition here is that what this transformation does, what this Mellin transform does, is that it trades this basis of momentum eigenstates for a basis of boost eigenstates, namely boosts. It diagonalizes boosts in the directions of the particles. So this a little bit of motivation for this transformation. You may wonder, so how do you see this? Where there are many ways to see why this is the case. But perhaps one more or less simple way to see this, which connects it also to this subject of soft theorems and asymptotic symmetries, is by studying the subleading soft graviton theorem. So on the left-hand side, we have a scattering amplitude of n+1 particles. So here, n of the particles are arbitrary particles, and we take one particle to be a graviton of momentum q. And what the soft theorem tells us is that as we take the limit, as the energy of the graviton goes to 0, this n+1 point amplitude is related to the amplitude without this graviton, so an n-point amplitude, up to a factor. And this factor is the so-called soft factor, whose leading piece is the standard Weinberg's soft factor, which has a pole in the limit as this energy goes to 0. So omega is the energy again of the graviton. Now these other two terms, S1 and S2, are the subleading and sub-subleading soft graviton factors. And importantly, one can think of these three terms as an expansion in powers of omega. So while the leading term has a pole in omega, the subleading term is order 1 in omega, the sub-subleading term is order omega, and so on and so forth. But these three ones are interesting in gravity because they're actually independent of the theory. There's also, of course, sub-leading corrections and so on and so forth, but those would depend on the particular theory you're studying.
Can you clarify what you mean when you say they're independent of the theory? For instance, are we talking about tree level?
I'm talking about just the pure gravity. It can be shown that
what does it mean to say that something is independent of the theory if we're fixing to pure gravity?
Oh, I'm sorry. I'm talking about, gravity coupled to any kind of matter, basically. These factors take the same form in any such theory.
But is that including loops or not including loops?
Including. So, okay, at tree level, it's definitely a statement, but there's been some papers by Ashok Sen and collaborators who actually studied this problem at all loops. And there is strong evidence that while they receive the subleading and sub-subleading soft factors, receive in principle corrections like infrared divergent ones and so on and so forth, but they take the same form irrespective of the matter content coupled to gravity.
But S0 doesn't.
I guess a question is there
Is the expression you're writing in some double expansion in powers of G Newton and energy, or sort of what sort of expansion?
Let me. So first of all, perhaps since it's not super relevant for the talk, at tree level, this is definitely a true statement. There is issues about loop corrections, and there is indeed the leading soft. I think there's no question that the leading one can do a diagrammatic analysis, and the leading soft factor actually is exact to all loops or all loop orders. The subleading soft factor is known to receive one loop correction. So the corrections are one loop exact. So a power counting basically shows that all the corrections one could have to the subleading soft graviton theorem in principle can only come from one loop diagrams.
Okay, thank you.
And for the subleading, there is a statement about two loops, but here, I mean, let's just restrict to tree level. So certainly the statement about the stress tensor, which I'm going to mention this relationship to the stress tensor, or to some object which looks like the stress tensor in conformal field theory is certainly derived from a tree level analysis. There's actually corrections, and one can either show that one can renormalize the stress tensor to absorb those and keep this identity invariant, or perhaps one can work in a different basis where there are no infrared divergences, in which case the statement would be exact. I think it's not fully, or at least it wasn't as of 3 or 4 years ago, understood whether there are finite corrections. But I think Ashok Sen and collaborators, they have a bunch of papers where they're arguing, I think, that these are, all these factors are pretty universal. So this is what I mean. But in any case, here, if we restrict it to tree level, I think there is that these are unambiguous.
Okay.
Does this answer the question?
Mm-hmm. Yes, thank you.
Okay. And so in fact, it's not gonna, I thought that this may be like a perhaps like nice motivation for why we're considering celestial amplitudes. It's actually not gonna be super relevant for what I'm gonna be saying in this talk. But okay, so but the idea now is that one can project out or kind of eliminate this leading piece by acting with this projector 1 plus omega d by the omega, which kills this pole in omega, such that one ends up with a relationship which just involves, which on the right-hand side would start at order 1 in the energy of the graviton. And so upon acting with some differential operator on both the left-hand sides and the right-hand sides, and upon performing some integral over the sphere, one arrives at some relationship which looks very much like the insertion of a stress tensor in a two-dimensional conformal field theory. So again, here I'm just relabeling. So all of the asymptotic states can be labeled, as I said, by an energy and 2 angles. So this is all I mean by this O1 of omega 1, Z1, Z bar 1. And this TZZ is whatever one gets basically from taking this soft limit, acting with this projector, and also in addition acting with these derivatives is some operator which is constructed from some subleading soft graviton mode. And there is an explicit expression for it, but it's not relevant for this talk, so I'm not going to go into that. But the point is that, okay, and the same procedure acting on the subleading soft factor with all of these derivatives and integrating gives the right-hand side, which can be massaged into this form of this factor, which is characteristic of the insertion of a stress tensor in conformal correlator.
Can you clarify, are you talking about something with Virasoro symmetry or just SL2C?
So here, this is a statement about this. I would say that this, I mean, the story about the subleading soft factor in gravity is actually an indication that the SL2C symmetry is enhanced to full Virasoro. So here we're talking about gravity, where it was shown by Andy and Dan Kapitz and Sabrina and Slava Lisov. They showed that this subleading soft graviton theorem can be obtained as a ward identity associated to some charges which are labeled by a function, by holomorphic functions on the sphere. So in this sense, there is an infinity of charges, and these charges are supposed to enhance the SL2C in gravity to full Virasoro. So, but again, here is just motivation. In the rest of the talk, I'm going to not restrict to gravity, and we're going to be talking about quantum field theories where we don't have a stressed tensor, and so like all we know is that Lorentz symmetry SL2C will be sufficient for the rest of the talk. Does this make sense? Okay, so okay, but this looks like the word identity of the stress tensor, but the point I wanted to make here is that the weights, the would-be weights of these external operators don't take the standard form as in conformal field theory. They're, in this case, they're operators, right? You would expect them to be numbers, they're here operators. And you may wonder, well, would these amplitudes diagonalize this omega I by the omega I? And of course, standard momentum amplitudes would not do that, because one can think of them as being just polynomials in the external energies. And of course, polynomials, if you act with this operator on a random polynomial of these omega i's, you're not going to get back the same thing up to a constant. So in order to make this problem more similar to a conformal field theory, one would like to find the basis in which these weights become diagonal. And this is exactly what celestial amplitudes do. So they provide the basis which diagonalize these weights. So I should say that these weights, actually, they're pretty natural. They arise. So the subleading soft factor has an explicit expression in terms of angular momenta from the bulk point of view. And it turns out that this omega I by the omega I is nothing but a boost in the direction of the particle of momentum pi. And so diagonalizing this omega I by the omega I is like diagonalizing that respective boost. And taking these Mellin transforms with respect to these external energies actually does the job. And you can see that by taking a Mellin transform of something like omega j by the omega j acting on the momentum space amplitude. Then you can integrate by parts, and you see that one finds an expression of this form, which then says that, okay, in this basis I introduced before, where one takes Mellin transforms with respect to the external energies, these weights, these HIs, become diagonal. So this is all I wanted to say about the subleading soft theorem, is that it provides some motivation for using this basis. And in fact, afterwards, Pastersky and Shao and Andy also, they showed, they studied this basis more generally. And for example, they showed that it provides a basis in which one can expand plane waves. And to see that, one can just Mellin transform this a plane wave. One finds an explicit expression in terms of, so
Anna? Has my audio gone, or
nope, she's gone.
I can't hear anything.
Anna, I think you were okay. It sounds like you're back.
Oh,
great.
I'm sorry.
Oh no, I think we just lost you for a few minutes or seconds.
Okay, thanks for. I was talking. So I was saying that Pastersky and Shao showed that plane waves can be expanded in this conformal primary basis. So they're just an alternative basis in which one can express scattering amplitudes, and they found explicit formulas for how these look like. So I was saying that this X labels a point in Minkowski space, and this little x labels a point on the celestial sphere. And in order to construct celestial amplitudes, one can alternatively just take the Fourier transform, the inverse Fourier transform of the momentum space amplitude or the position space amplitude, and integrate it against these wave functions. And this is how one gets to this expression more formally. And moreover, they also studied, I mean, the way these are by construction, they transform as conformal primaries under the global, under SL2C, so Lorentz group. And moreover, they showed that if delta is restricted to take the form 1 plus I lambda, so in 4 dimensions, 1 plus I lambda, more generally, it would be d divided by 2 plus I lambda, then these wave functions also form a complete normalizable, like a normalizable set. Now, this restriction is not going to be relevant to this talk because, as we'll see, translations move you off this so-called principal series. And also, things like the stress tensor also have dimensions which are not of this form. The stress tensor would have spin 2 and the dimension 2. So, okay. Now, some properties the celestial amplitude obey are the fact that by construction, as I just said, they transform covariantly under the Lorentz SL2C. More interestingly, they transform non-trivially under translations. So in addition to global conformal symmetry, generally we, in Poincaré invariant theories, one also has these translation generators, which on the celestial sphere act by shifting the dimensions of these states by 1. So this can be seen again because translations from the momentum space point of view are proportional to the energy, and factors, multiplying the momentum space amplitude by factors of omega upon taking a Mellin transform can be seen to actually amount to shifting the dimensions on the celestial sphere. This factor epsilon I here again labels whether the state is an incoming state or an outgoing state. It's just a sign. So translation invariance from the bulk point of view then implies a non-trivial relationship on celestial amplitudes. And this was demonstrated by Stieberger and Taylor and Lyons-Lotnikov, who showed that, I mean, it's not hard to translate momentum conservation for celestial amplitudes, right? It's just going to take by acting with the sum from I equal to n, from I equal to 1 to n of momenta on the celestial amplitude, one finds a relationship between amplitudes with dimensions shifted by 1. And this has, all of them have to add up to 0. This is just translational invariance.
So just to make sure, this is without taking any soft limit yet. This is the exact statement. Am I right?
Yeah, it's the exact statement about
celestial
amplitudes.
Got it. Thanks.
Yeah, thanks. Okay. So, but that this constraint is non-trivial was shown. So I should say this symmetry was pointed out by Stieberger and Taylor. That this Poincaré constraint, this full Poincaré constraint implies a non-trivial constraint on celestial amplitudes was shown by Lyons-Lotnikov 2 years ago. So if one restricts to 4-point scattering, we see that these two properties have to imply that the celestial amplitude takes the following form. So here, this is just the standard SL2C covariant prefactor, which multiplies conformal 4-point functions, also familiar from conformal field theory. Now, this f of delta in z is actually is the expected, again, it's the expected function of the cross ratio, which is conformally invariant. Now, the added constraint from translational symmetry is that this object cannot be an arbitrary function of the external dimensions, but it has to depend on only the sum of the dimensions of the external particles, again, for 4-point amplitudes. And so, okay, that's an interesting property obeyed by celestial 4-point functions in contrast to usual conformal correlators. Now, another constraint celestial amplitudes have to obey comes from soft theorems. And here is one example. So this is one way, using these parametrizations of the momenta I had before, this is one way of writing the leading soft theorem. which can be also translated to the celestial sphere. So a priori, it's not completely obvious that celestial amplitudes would also obey a soft theorem, because remember, from the momentum space point of view, soft theorem involves taking the limit as the energy of one of the external, photons or gravitons or gluons or whatever, as that energy goes to zero. But there is no sense in which one can take an energy to zero in celestial amplitudes. Nevertheless, it can be shown that soft operators actually can be constructed by taking the residue of a celestial amplitude as the dimensions take integer values. So in particular, the leading soft photon theorem would be extracted by taking the limit as delta, in this case, delta 0 goes to 1 of the celestial amplitude. And this is exactly, this will reproduce, this will actually amount to inserting a soft, or a conformally soft photon in this amplitude. And more generally, there exist towers of soft currents, which are associated with insertions of increasingly negative delta. So for example, a delta equal to 0 operator, depending on the spin, of course, also can be a subleading soft photon or a subleading soft graviton, and so on and so forth. And it was shown that, in fact, while the leading conformally soft theorem is very similar to the momentum space relation, the subleading and sub-subleading soft theorems actually impose more non-trivial constraints on the celestial amplitudes, in that just like translations, they relate celestial amplitudes with operators of differing dimensions. So both the subleading soft factor and sub-subleading soft factors, they shift these dimensions. This can be shown, and the corresponding symmetries, if one, for example, writes down an OPE for gluons and gravitons in Einstein-Yang-Mills theory, one can use these symmetries to constrain the leading OPE coefficients.
What is meant by an OPE in this context?
So in this context, it would just mean literally the collinear. If you have a momentum space amplitude, you know that it obeys not just soft theorems, but also collinear theorems. And so a collinear limit would be the limit in which two insertions on the celestial sphere approach one another.
Can I also ask one question about the big picture here? So you take the momentum space amplitude and did the Mellin transformation, and then provided it is an invertible transformation, looks like they should keep the same amount of information, but it may just be that if you go into this space in terms of boost eigenstate, you may get different insight about the structure of the amplitude, especially soft theorem statement can be translated into, for example, different statement that you're trying to explain. Now, is this basically what's going to happen, or you actually are supposed to get more information by going into celestial language than momentum amplitude language? I'm just trying to understand.
It's a great question, and I think ultimately we'd expect, if we knew all of the constraints, since amplitudes actually, in some sense, celestial amplitudes in some sense contain non-perturbative information. If you knew all of the constraints in a similar flavor to the bootstrap program in conformal field theories, one may expect to be able to just impose those constraints and then deduce new information about the momentum space amplitudes, or the structure of quantum gravity amplitudes, and so on and so forth. So I mean, that would be the ultimate hope. Right. But right now, nothing I am going to say in this talk will be of that nature. So in this talk, we're going to take the opposite perspective, namely, we barely started to understand these celestial amplitudes, and we are just trying to understand what properties they have to obey. And right now, all we have at our disposal is this map to the momentum space amplitudes. So we're going to see that known properties of momentum space amplitudes actually translate into interesting constraints on celestial amplitudes. But of course, ultimately, you'd want things to go in the opposite direction, as you're saying.
Right.
But this I was just mentioning because I think it's interesting. Perhaps is, I don't know, perhaps is expected. I thought it was interesting because there's been some work by Stieberger and Taylor, or Fan and Fotopoulos, who showed that, you know, you can take a momentum space amplitude, take the collinear limit, then do a Mellin transform, so put it on the celestial sphere, and actually this collinear factorization can be translated into some OPE-like relation on the celestial sphere. But what we showed in this work with Monica Pate and Andy Strominger and LSU1 was that one can make no reference to momentum space and start off with an OPE of gluons and gravitons, whose leading piece is actually fixed completely by SL2C, and determine this leading coefficient by imposing these subleading soft theorems. So leading soft theorems were not enough. It was important that one used subleading soft theorems in gauge theory and subleading soft theorems in gravity. Those were the ones which gave these non-trivial recursion relations, which we are able to use to actually constrain these OP coefficients, which, by the way, they're given in terms of Euler beta functions, which are known to obey and be completely determined by recursion relations. So something of that nature is I think what one might hope for.
Okay, thank you.
Okay. Okay, so this was, okay, can you see the new slide now?
Yes.
So this is sort of the end of the motivation, and in this talk, I'm gonna show that there are additional constraints which scattering on the celestial sphere has to obey. So in particular, we're going to be restricting to 2-to-2 scattering. So this is the simplest example one can think of. And we're going to show, so we already saw that these 2-to-2 amplitudes are constrained to be functions of sums of the external dimensions. And what we're going to see is that they have a simple analytic structure in this complex delta plane. So again, this delta is the sum of all of the external weights. So in particular, we're going to see that the poles, there's going to be poles in this complex delta plane, and these poles are going to be confined to lie on the real axis at even integer values. And in particular, half of these poles are going to be erased in quantum gravity. And this erasure actually arises from the exponential suppression, the expected exponential suppression due to black hole creation in quantum gravity. So this is the main ingredient which ensures that celestial amplitudes won't have any poles on the positive real axis, as we'll see. Finally, hopefully I'll have time to briefly comment on the soft factorization on the celestial sphere and constructing infrared finite celestial amplitudes, as I briefly said at the beginning. Okay, so the setup again. So just to remind everyone of the notation, we're starting with a 2-to-2 momentum space scattering amplitude. So in momentum space, these are labeled by two Mandelstam invariants, which are independent, so S and T. So naturally, one expects that the celestial 2-to-2 amplitude is also labeled by two parameters. And these two parameters, as I hinted to before, are going to be this conformally invariant cross ratio, Z, which upon parametrizing momenta in the way I showed before, can be shown to be nothing but the ratio between the Mandelstam T and S. They're also going to be functions of the sum of the external dimensions, as argued before. Now, what is the precise relationship between the momentum space amplitude, which is a function of S and T, and the celestial amplitude? Well, that can be found by just starting off with the momentum space amplitude and performing this Mellin transform. So in this case, the delta function, this momentum conserving delta function, is pretty constraining. So there's going to be 4 constraints here, one of which is going to impose that the cross ratio is real which is expected. It's an expected feature of momentum conservation in the bulk. We know that scattering in the bulk has to happen in the plane, and this plane has to cross the celestial sphere on some circle. And this is the circle described by z equal to z bar. And then the other three constraints actually impose that all of the external energies have to be proportional to one another. So remember, we have 4 Mellin transforms here, one with respect to each of the external energies. 3 of those are going to get saturated by these 3 constraints and are going to give rise to a prefactor which precisely ensures that the celestial amplitude is conformally covariant. And at the end of the day, and also we're factoring out this delta function of z minus z bar. So that would be in this factor I'm dropping here. But the remaining piece is just going to be a Mellin transform with respect to some energy variable, which we're calling omega, where now this beta here is actually the sum of the external dimensions minus 4. So it's basically the sum of delta I minus 1. Of the momentum space amplitude evaluated at s equal to omega squared and t equal to minus z omega squared. So this is the main relationship we're going to be using in the rest of the talk. So it's a direct map between the momentum space 4-point function and the celestial amplitude. But as we can see, it depends on both beta and z, right? Now, one simple example one can consider is what happens if the momentum space amplitude is just the power of the energy, as it would be, for example, if one starts to do a low energy expansion of this amplitude. Now, if one considers one term in this expansion and takes the Mellin transform, you immediately see that you get an answer which blows up, right? I mean, for generic values of beta and p, this integral is highly divergent. And the only case in which one gets a more or less sensible answer is when beta is equal to minus p, both imaginary, in which case this integral can just be seen to give a delta function. So it's just the inverse Fourier transform of a delta function. So on the other hand, so we already see that we need some kind of input about what happens in the UV in order to have well-defined celestial amplitudes. And this is what we're going to be studying next. So to see how this comes about, we can consider a simple example of massless 2-to-2 scattering mediated by the exchange of a massive scalar of mass m at tree level. In this case, the tree level amplitude is going to be a sum over ST and U channels. So let's just restrict to the S channel for now. To see how the celestial amplitude has to behave. And so the problem just reduces to taking this Mellin transform of a function which has a pole in omega squared at m squared. Now this integral can be evaluated directly by counter integration. You can also read off the answer from a table of Mellin transforms or whatever. So at the end of the day, one finds that this Mellin transform gives a function proportional to 1 over sine pi beta divided by 2. So this tells us that the celestial amplitude has an infinite number of poles at even integer beta. Okay, so this is one first simple observation, that poles in momentum space translate into an infinite number of simple poles in the complex beta plane. So to understand these poles better, one can take this momentum space amplitude and do an expansion around low energy. So of course, this expansion will only be valid in some range of omegas. So we're going to cap off this integral here at some omega star where this expansion breaks down. And so then term by term, one can then see that each of these terms in this expansion of the momentum space amplitude translates into a pole at beta equal to minus 2n, where n is a positive integer. Where n is a positive integer. And moreover, the coefficients, which would be the residues of these poles, are directly related to the coefficients in this expansion. So this is an expansion in S at fixed t divided by S, if you want, in momentum space. And so in other words, so these coefficients are also directly related to coefficients in low energy effective, in the low energy effective field theory, right? And so these residues are then directly related to the effective field theory, these effective field theory coefficients. Now, similarly, one can do the same expansion of this function around S going to infinity, in which case all we have is like these coefficients are going to be replaced by some AUV, and this expansion in powers of omega is going to be replaced by an expansion in powers of inverse omega, which is then going to give a celestial amplitude with poles at beta equal to 2n instead for positive n. And so we see that an amplitude which admits an expansion around large S also is going to have poles, but now not on the negative real beta axis, but on the positive real beta axis. Okay, so this was a gauge theory amplitude. The next example is an amplitude in quantum gravity. And so the toy model here is that we have 2-2-2 scattering in gravity. Say 2 gravitons going to 2 gravitons. And here we're talking, this is a non-perturbative statement about how this amplitude should be looking like. So we know that as we pump up the energy, as we increase S for fixed T, we're gonna make a black hole. And so the number of black hole microstates is expected to grow as the exponential of the black hole entropy. And so we expect that this process, so this particular 2-2 scattering process, is going to be, roughly speaking, suppressed by the inverse of the number of microstates, which is something proportional to e to the minus black hole entropy. Now, if the black hole entropy scales as the area, namely goes as omega squared in units of m blank, then as omega goes to infinity, so at very large energies, this is like large S limit, we expect the amplitude to be exponentially suppressed. So it goes as e to the minus omega squared divided by some m squared. So here we're absorbing possible factors in this constant here. And so, but the main point is that if one considers the Mellin transform of such an exponentially suppressed amplitude, one finds this is the standard Mellin transform of an exponential, is a Euler gamma function. And it's well known that this gamma function has no poles on the positive beta axis, but again has poles at when the arguments are negative integers, right? And so like, again, we see that we still see the low energy poles here. So the poles at beta equal to minus 2n, they survive for positive n, but the other ones are erased. And so we expect this more generally whenever one has an amplitude which is exponentially suppressed at high energies, we expect these poles we saw before on the positive real beta axis to be erased. This is another result. Okay, and finally, just 2 more comments about loop amplitude. So I wrote down an expansion in powers of omega before for the low energy amplitude, but we know that this power series in omega is actually dressed by logarithms if one takes loop effects into account. But these loop effects have, again, a nice interpretation on the celestial sphere. And they actually show up as higher poles in beta. Again, it's a simple observation that if one takes the Mellin transform of some power of the logarithm, that's the same as taking alpha derivatives with respect to beta of this kind of integral. But we saw before that this is like a pole a simple pole in beta. So taking alpha derivatives with respect to beta increases the order of this pole by alpha. So in other words, higher order poles in beta contain information about loop corrections. And finally, one other fact is that if one has a theory in which one has several massive particles, like in the first example I considered, but with several scalars of mass m being exchanged, then the celestial amplitude is going to take the same form as we found before for one massive exchange, but with a sum over all possible exchanges. And what we see is that as we take the limit as beta goes to minus infinity, the sum is dominated by the lowest mass exchange. So this is another feature of celestial amplitudes. And it's relevant because, I mean, one can study amplitudes, tree-level amplitudes in string theory, which, by the way, their celestial versions are actually quite complicated and not known actually in full analytic form. Nevertheless, one can use the expressions which have been written down by Stieberger and Taylor for these string amplitudes, the celestial string amplitudes, to actually verify that they obey all of these properties I talked about. Well, except there's still, in that case, there is some exponential suppression, but it comes from, you know, softness of these tree-level amplitudes because of the infinite number of massive string states. But yeah, in any case, they do obey most of these properties. All of these properties actually I discussed so far.
Can I
Yes,
ask one quick
please.
question? So in previous two slides, you showed that in the field theory example, in the limit where s goes to infinity, in the case of pure scalar field theory example, you show that there is a negative, positive pole appeared in the beta in terms of beta, but then in the quantum gravity example, you show that actually you don't get to see those poles. So in terms of momentum space language, then you might be saying that, so in the momentum space amplitude, we expect that, naively we expect that as long as amplitude does not grow more than, say, s times log of s or something like that, we might think that it is consistent. But quantum gravity seems to suggest that actually amplitude must dies off as fast as the e to the minus s, roughly speaking.
Right.
So there should be some sort of turnover in order to be consistent with quantum gravity. Is that the
Yes.
story about the beta is the equivalent story about this statement?
This is the point I was trying to make. Yes, this was a good summary. Thank you.
Okay, thanks.
Okay, any more questions? Because I'm now going to switch to this other IR piece in the remaining 10 minutes or so. Okay, so now that we looked at some of these UV aspects of celestial amplitudes, we can also ask the question, well, what happens to known things we know from momentum space about the IR? And one of the natural things to be looking at is QED, where we know since Weinberg that infrared divergences exponentiate. So first of all, in a 2-2-2, so here we're considering a toy model of massless QED, where we have some kind of electron-positron scattering in this context. And we know that to all loop orders, this process suffers from infrared divergences, and these infrared divergences come from low energy photons exchanged in the loops. What Weinberg has shown is that actually one can sum all of these ladder diagrams and show that the infrared divergences exponentiate and set the momentum space scattering amplitudes to 0. So here, the exponentiation, there is a piece, which is, I'm calling e to the b here, which is the soft kind of part of this amplitude. And m is the free of IR divergences part of the amplitude, so the hard part of the amplitude. And there is a formula for b. So the sum is negative. So actually, as one takes lambda IR to 0, one can see that this b goes to minus infinity, and so e to the b goes to 0. Now, there is an analog. One can again ask the question, well, what happens if we put this on the celestial sphere? And again, all one has to do is to consider a Mellin transform with respect to all of these external energies.
Sorry,
And
can I ask a question about the comment on the previous slide?
Yes.
So when I was learning field theory, I was also taught about a whole series of processes where there are additional Bremsstrahlung of
Yes.
soft photons.
Yes. Yeah.
So where in this formalism is that? I mean, that if you, of course, if you're restricting yourself to 2 particles in the out state, that's absent. But
yeah. So let me say, maybe I should have said, I was going to say this a bit later, but you are totally right, right? I mean, if a 2-to-2 scattering process in conventional QED is actually badly IR divergent, but the resolution, as you're saying, of this problem in textbook quantum field theory is that in order to make this process, to extract some finite information from this process, one has to look at cross sections instead. And namely cross sections where one has an arbitrary number, one is supposed to sum over cross sections associated to processes where there is an arbitrary number of soft photons in the out state, for example, right? And that's supposed to, I mean, that has been shown, and not it's supposed to. I mean, it can, in this case, one can extract IR finite information. Okay, but here there is an alternative prescription, which was given by Fadeev and Kulish and Chung and Kibble, where one can actually define infrared finite, or at least they claim that one can define infrared finite scattering amplitudes by actually computing. Again, their idea is that the basis of eigenstates one computes the S matrix typically in is not the right basis, because the intuition is that electromagnetic interactions are long range and similarly in gravity, and so like one always has some kind of like soft photons in the in and the out states, and so in order to build infrared finite observables, one has to account for them, and so it has to modify the basis of asymptotic states to include these coherent clouds of soft photons or gravitons respectively. And again, that has been shown, or I mean, there is some debate, I think, in the community of like, there are issues with that formalism, but I'm going to say one simple thing about why, or at least why we hope that the celestial amplitudes may solve the issues people have been complaining about in that construction, this Fadeev-Kulish construction.
Well, at least the amplitude going to 0 is now quite physical, right? So you are, if I take your formula literally,
this is the undressed
amplitude goes to 0.
Yes, but this is the undressed amplitude, so this is what I've been saying. I mean,
yeah. So it's not quite a physical.
No, but yes, I'm not saying that this is a physical process. I'm just
presumably this amplitude, this writing it this way is good for something else, but not to directly connect to observables.
No, but this is not. I'm not going to connect this to observables. What I'm going to connect to observables is going to be these dressed amplitudes. But I was just like saying some words about the usual story. Like these are the sick ones, but this is. Yeah, so this stuff here is also suffers from the same problems. But in the next slide, I was going to describe the addressed amplitudes, which are supposed to be good observables. And there is a nice interpretation of those. I mean, in particular, there is one choice of Fadeev-Kulish dressings, which is singled out on the celestial sphere. So I'm not sure if this answers the questions. But.
Yeah, so you're saying that this particular parametrization of amplitudes is maybe a nicer one for addressing this issue.
Yeah, exactly. And the reason why it's not, okay, I'm going to say, maybe I don't have that much time left, but perhaps I can just go through the slides.
Yeah, let me shut up and let's continue and get to
I hope it's going to answer
formulas.
Okay, there is not that much but left, but anyways, so we have, all I wanted to say here, this is to build up this discussion of dressed amplitudes. I'm just making, this is an observation by actually like Andy and Angelica Nande and Monica Pate. They showed that the soft hard factorization can be reproduced by well, they didn't work in the celestial framework, but nevertheless, they showed that the soft part of the scattering amplitude can be reproduced by some kind of correlation function of vertex operators associated with free bosons, these phi's. So this is standard thing. And here we find that, so this remains unchanged, but the added, now on the celestial sphere, what happens is that the hard part of the celestial amplitude now involves some kind of operators or asymptotic states with dimensions which are now shifted by a term proportional to this cusp anomalous dimension. So this is needed. I mean, this is to ensure conformal invariance based SL2C invariance of this A tilde of this full celestial amplitude, right? Because this factor carries some dimension, and so like if one Mellin transforms this object with respect to delta i's, which are unshifted, these are the original delta i's, one needs the hard amplitude now to be expressed in terms of some kind of shifted weights to absorb the factor one picks up from the transformation of this of this correlator. And so anyway, so this can be shown by just noting that the pi.pj takes this form, and just doing these Mellin transforms. And also charge conservation has to be used in this calculation. Okay, so, but this is not what I wanted to say. I wanted to say that the dressed, actually, I was hinting towards this before. So in QED, Chung, Kibble, Fadeev, and Coolidge proposed that one can construct infrared finite scattering amplitudes, not cross sections. I mean, cross sections is one way to look at the problem, but one can also look at the perhaps more fundamental building blocks, namely scattering amplitudes, by computing them in a basis of coherent states. So namely, one takes these the usual momentum space asymptotic states and dresses them by these coherent clouds of soft photons or gravitons in gravity, right? So these A's are creation annihilation operators for the photons, and these are integrated against some function, which is the soft factor. This F here is typically in these analysis is like a step function around, and not the top hat function, sorry, around some small energy range, such that this exponential only typically includes soft particles and not all energy particles. But the problem with that approach, right, is that different functions, there is an arbitrariness in choosing this function. Any choice of this function pretty much, as long as it doesn't have a pole, as long as it's order 1, as q goes to 0, any kind of function gives a state in which infrared divergences go away. Most choices break Lorentz invariance, right? Because you're going to introduce some kind of cutoff on the energies of the photons allowed in this cloud. But what we're going to show here is there is a natural, on the celestial sphere, there is a natural choice for this exponential, for what's in here, which involves photons of all energies. Now, in momentum space, that thing doesn't make any sense, because in a finite, if you're colliding particles of finite energy, you're never going to be able to emit like photons of arbitrary high energy, right? So taking the energy to infinity in standard momentum space basis doesn't make much sense. But in the celestial basis, right, we are working with asymptotic states, which involve integrals over all energies. And so considering these exponentials to involve all energy photons actually does make sense. And so in particular, one can show so based on some work by Laura Donnet, Andrea Poom, and Andy Strominger, who identified the canonical partner of the soft photon. So this J here stands for the celestial, the so-called conformally soft photon. It has a canonical, and I should say this thing on the celestial sphere is an operator, or translates into some operator of dimension 1 and spin 1. There is, though, a canonical conjugate to this operator, which has the same dimension and the same spin, and this was shown in this paper here, which means that the quantized electromagnetic potential has an expansion in conformal primary modes, which takes this form here. So as at the beginning, I argued that conformal primary wave functions for delta equal to 1 plus I lambda form a complete set of states for plane waves. So this would be just the usual plane wave expansion, but one has to also take into account at least these soft modes. So these are delta equal to 1 modes, which they're not including in this other integral. So they're writing down explicitly. And so by looking at this expansion, one can then see that by taking Klein-Gordon inner products of this quantum field with either this function here AG or ACS. So I should say these are the conformal primary wave functions associated to these delta equal to 1 modes. So AG is the pure gauge quantity, while ACS is roughly speaking AG multiplied by a step function in U. So it's like a shock wave-like solution to the free Maxwell equation. They're both canonically conjugate. One can show that if you take the Klein-Gordon inner product of these two solutions, one gets a delta function, which also implies that, as I said, this J is canonically paired with S. And so this collection of facts allows us to extract both the conformally soft photon characterized by this J and the so-called Goldstone mode labeled by this Z by taking these inner products of A hat with these conformal primary wave functions. And so the punchline is that actually this Fadeev-Kulish dressing can be reproduced as an exponential of this Goldstone mode phi, which is directly related to this this partner of the conformally soft photon. So this can be shown explicitly, and this is what it did in this paper. So just one comment: there is a way to now basically there is a prescription of how one can construct infrared finite celestial amplitudes. Which is namely to consider celestial correlators of these operators O hat of dimensions shifted by the square of the charge multiplied by this this alpha. So all of this actually follows from both this soft hard factorization. And well, basically, all of this just follows from soft hard factorization. That implies some sort of OPE between this exponential of the Goldstone and some undressed operator of this form. And so one can then consider the normal ordered version of this expression and define these O hats operators in this way. And one can show that this then just reproduces the hard part of the celestial amplitude. And one can also show that these ideas just by very similar calculation can show that everything holds in gravity as well. So, okay, so I think I'm running out of time. So just to sum up, we showed that there is celestial amplitudes have some interesting properties, both coming from the UV and the IR. So of course, there are a lot of open questions. I would say that one important one, which somehow seems like it should be obvious or I don't know, easy to do, is to generalize all of this to theories with massive external particles, but somehow it seems to be a bit more non-trivial than we thought, but I think everyone expects this to work, so this would be a natural next step. Now, one interesting question is whether one can use all of these constraints on celestial amplitudes to actually determine 2-2 graviton scattering amplitude in full quantum gravity, for example. Another question is about what the spectrum of the celestial field theory is, what is the operator algebra. This kind of question can be addressed by actually studying a complementary part of these 2-2 celestial amplitudes, namely the Z dependence, this dependence on the cross ratio. So in some work with Alex Atanasov and Walker Melton and Andy, we've been looking at this problem a bit, and we have some understanding about conformal block decompositions of celestial 4-point functions and so on and so forth. But the story is a little bit less clear there. And then there are some other interesting questions, many which I haven't listed here, but since I think I'm basically out of time, I should stop and ask if there are any questions. Thank you.
Thanks very much, Anna Maria. A very stimulating talk. I will clap for